Good day, everybody. I hope everybody's doing well. We are about to get into the thick of the course, the meat and potatoes of the course, where we are going to be covering a whole bunch of different kinds of algorithms to solve a bunch of specific kinds of problems. The first kinds of problems that we're going to get into for the next few lectures, in any case, are going to be those that work on root finding for different kinds of functions. And there are a few different methods to do this. Some are more efficient than others, some work in some cases where others don't, and we're going to talk about each one of them, hopefully in their own videos. So I guess we're going to get started and talk about the basic problem for now, and that is to cover what do we mean by root finding methods. So I mean, the language is nothing different than what you might already know from high school or first year calculus or functions. Um, we're going to be finding roots of a function f of x, and a root is nothing more than a specific value such that when you put it into the function, you get out 0. So root finding comes up really commonly in everyday math applications. Sometimes we have the ability to solve these things, but sometimes we don't, especially for kind of complicated and non-linear equations or equations that are involving like strange functions and so on. There aren't really any simple or straightforward classical approaches to accomplish this. What do I mean by that? Well, if you have a quadratic equation, a second degree polynomial, you might be able to find its roots, if they exist, by using the quadratic formula. That is an approach that you would have learned in high school. But it turns out that if you go up high enough in degree, there don't exist any formulas anymore. There is actually a formula to find the roots of a cubic, and even a quartic. But once you get to 5th degree and higher, I believe it's been proven that there are no closed form formulas in order to determine what those roots are. So what the heck do you do if you still need to find them? And that's not to say, there aren't a whole bunch of other kinds of functions out there as well that aren't even polynomial that maybe we cannot solve. So finding roots is actually useful in solving a whole lot more problems as well. Suppose you're given any equation, and that equation has a function on each side. So f of x on the left, g of x on the right. We can actually solve that equation by instead finding the roots of the related function f of x minus g of x. That is itself a new function, the subtraction of the two, where that subtraction is equal to 0, those are exactly the x values that will solve the original equation. The roots of f minus g are the solutions to f equals g, and that should make some sense. So suppose we wanted to know the values for x, of x, which would solve this equation right here, that involves a bunch of awkward roots and stuff. And we wanted to know where the left-hand side was equal to 2. Rather than solve this equation, we could instead find the roots of the function 5th root of x minus 3rd root of x plus x minus 2. And if we find the roots of that equation, we solve the original equation. That should make some sense. Okay, all of the methods that we're going to cover in this section are what we call iterative. What does this mean? Well, if you iterate something, it means you repeat it many, many times over. So it involves a process that's repeated again and again, and you get a bunch of estimates of an answer until some ending criteria is reached. That ending criteria can differ. After many iterations of the method, perhaps the estimates stop changing very much at all, indicating that the estimates have converged. Maybe your estimates have gotten closer and closer and closer to the right answer until like it's so close that they don't even change very much. Okay, so if, in other words, if two consecutive estimates are close to one another within some tolerance, you can call it whatever you want, I use delta right here, you might terminate a method, having found a possible solution. Okay, perhaps, after some set number of iterations have been executed, you still don't have any clear answer. What happens if you iterate a method, you repeat a calculation 100 times over, and you're no better off than where you started? What's the thing you do? Well, like all good mathematicians, we give up. I don't actually advise that. but you can give up on using that method because maybe there is another method that you could try to solve a problem. We're going to find that sometimes there are some methods that simply won't be good for solving certain problems, whereas other methods will be. And you might want to change gears and try using a tool. Instead of trying to keep using the same tool and bashing your head against the wall, maybe you can try to use something else to bash against the wall, and maybe you keep your skull intact that way. I don't know. Okay, so there are a bunch of different ways that we might stop a method. And that might mean that we found a solution, or maybe it means that we didn't find a solution. And when you're building code, when you're building an algorithm, keeping in mind some ending criteria is really important. Okay, so I said root finding is where we're going to be at. There are actually 4 methods we're going to talk about. The first of those methods is one that's called the bisection method. This is pretty much always where this conversation begins in any numerical methods course, because it's a pretty simple method and it relies on one of those things that we covered in the very first lectures, intermediate value theorem. So here's the criteria we need for bisection method, which I kind of like to call intermediate value theorem on steroids. So suppose that we know that a function f is continuous on a to b, so it still has the criteria for intermediate value theorem, and you know that f of a and f of b have opposite signs, as we know must be the case for intermediate value theorem, then that theorem holds. And what does it say? It says that there has to exist a root. If on one side the function's positive and on the other side the function's negative and it's continuous between the two, there has to be a 0 somewhere in between the two, at least one of them. Okay, we might not know exactly what that root might be. And in first year, we stopped. You know, you would say, okay, I know that a root's got to exist there. We're good. But we can actually do better. What we have at this point is a range of values that we know must contain that root. The main idea is, let's try to find a tighter range. And what we're going to do is repeatedly cut that interval in half. Sorry, I can't find my cursor. Cut the interval in half. That's where the bisection aspect comes from. So let's think about what this means in terms of the math. We're going to let a0 be a and b0 be b. So we're at the ends of our first interval. Okay, so a, b is our initial interval that we're interested in. All right, interval number 1. And let's see here. What we're going to do is test the midpoint of the two. So the average of the two, a0 plus b0 over 2. All right, that means we're going to take the midpoint of the initial interval and we're going to check to see if f of c is positive or negative. There are logically 3 possible things that could happen here. Because the f of c, right, the midpoint of that interval, when you put it into the function, it's got to be either positive, negative, or 0. So trying to put it in place here, that means that f of c is going to be either the opposite sign of f of b0, it's going to be the opposite sign of f of a0, because the a0 and the b0 had to have outputs that were opposite signs to start with. The other possibility is that that midpoint is actually the root itself, that f of c is actually equal to 0 itself, and thus we found a root c and we're done the problem immediately. That would be very lucky. That's not going to happen very often, because usually a lot of these kinds of functions will have a root that has, like, you know, an irrational number as the correct solution and so on. So you might never get there. But it is technically a possibility. So yeah, you have that either it's the opposite sign of one side, or the other side, or it's the root. Those are the only 3 things that could happen. But once you know that, suddenly, if you think about what that means that now you have a tighter interval where you have 2 sides that have opposite signs, right? You're going to have whatever the sign of f of c is, and then whichever one of the f of a, or f of a0, and f of b0, which one of those is the opposite sign of the midpoint. There's got to be one of them. Use that as your new interval and repeat the process. Keep doing that again and again and again and again. Because every single time, well, the original function had to be continuous, so any smaller interval has to be continuous. You're guaranteeing at every single point that you have endpoints of that interval that are opposite signs. So intermediate value theorem is going to hold every single time. And you can continue the process indefinitely until you get to as good of an estimate of the root as possible. So let's kind of try to make this a bit precise here. So we're going to define a new interval a1, b1 using c and whichever value of the a and the b such that f is at that value is the opposite sign of f of c. It will necessarily be half the size of the interval that we started with. And as I said, f will still satisfy intermediate value theorem. We know there has to be a root contained in it. And then we repeat the process. And due to the fact that every single time we have those three possible logical things, right, we can make that interval as small as we want. We can get as good of an estimate as we want. And so we're going to see how this works in an example. So here we have example 1, consider the equation e to the minus x equals x. Find an estimate for a solution to this equation by iterating bisection method 3 times using a starting interval of x in 0 to 1. I'm going to go back to the last sentence of the previous paragraph because I wanted to kind of indicate once you have done this process, right, you're shrinking an interval to a smaller one. An estimate could really be any number in that last interval. And so typically, you might consider the midpoint of the final estimate to be your final estimate. So that's what we'll assume in particular, but you might find that there could be times when, you know, the function at one of the endpoints is very, very close to 0, so you could choose really any point that you like. But we'll consider midpoints here as a general rule that will be pretty good. Okay, so back to this example. Yeah, we're going to have e to the minus equals x. That's the equation that we're going to solve. And the first thing I'm going to do is point you back to the first page of this section on root finding. To solve the equation e to the minus x equals x, we can find the roots of the related expression, or the related function, e to the minus x minus x. And if we find the roots of that, we solve this equation. So, i.e., we want to find the roots, and I'm going to define the function f of x equals e to the minus x minus x. If we do that, then we will have solved the original problem. Okay, so what are we going to do? Let's set this up. I've got a lot of the calculations here in front of me, so I'm going to have to refer to them. So we're going to start with our current interval. I like to be a little bit organized here, just so we're clear on what we're doing here. So current interval is 0 to 1, and what we're going to do is do what we would usually do for intermediate value theorem. We're going to test both endpoints, and f of 0 is pretty easy to see even by just staring at it. E to the 0 minus 0 will be 1 minus 0, which is 1. So f of 0 equals 1, and f of 1 equals negative 0.632 is what that works out to if you just plug 1 into that function. Okay, what we're going to do is test the midpoint. So we're going to test f of 0.5. And f of 0.5, if you work it out, is 0.1065, if you throw that into your calculator. What we're going to do is we're going to look at which of those 3 possibilities could happen. Which are the 2, including the midpoint, that now straddle the root? Which are on both sides? And the answer is going to be, well, this one here, 0.1065, and this one here, minus 0.632, those are on opposite sides of the root because I have one's positive, one's negative. Okay, so if those are on opposite sides, then those are the ones that I'm underlining. And that's one iteration. That's one iteration of bisection method. That produces a new interval, a new interval of 0.5 to 1. And I want to kind of keep a little bit track of some different things here. This is going to give a best estimate if we use that midpoint, as I said before, x equals 0.75. All right, so let's keep going. That's one iteration, and then we repeat. It says 3 times. So we're going to, I'm going to stay organized here. I'm going to use both of those sides. So f of 0.5, we already did this, was 0.1065. F of 1 was minus 0.632. And we're going to test the midpoint of those. The midpoint of those is going to be 0.75. So f of 0.75 is equal to, and you work that out, that turns out to be minus 0.277. So you stare at that for a second and you say, okay, we're going to have a smaller interval here. Underline the ones, keep the ones that are on either side of the root. There's a positive one, 0.1065. There's a negative one, minus 0.277. So our root has to now be between 0.5 and 0.75. It's like we're slowly narrowing things down a little bit at a time and chopping away the pieces and zoning in on what that root should be. So that's the end of our second iteration. So that's 2 iterations now. Our new interval is 0.5 to 0.75. And our current best guess at what the root is going to be x equals halfway between the two, 0.625. Although you could, again, as I said, choose anything within that interval, but we're just going to, for simplicity, choose the midpoint of the last interval as our best guess. Yeah, I guess we're going to do the third one down here. We'll do this one more time. So hopefully it's clear as day. I'll just repeat those calculations again. So this is f of 0. Which are the ones we're keeping? F of 0.5 and f of 0.75. Those minus 0.277. And we're going to test the midpoint of those. And that would be 0.625. We're going to throw that into the function. You could use fractions. It doesn't really matter. And if you put this into the function, you get negative 0.0897. Okay, and we're going to look at which ones are again on either side. It looks like this one and this one this time. And at the end of 3 iterations, that's 3 iterations, and our new interval is going to be between 0.5 and 0.625, and our best guess is halfway between the two, x equals 0.5625. You could repeat this again and again and again and again, and this is going to be our final estimate, because I only asked you to do it 3 times, but you could do this arbitrarily many times to get as good of a root as possible. So our final estimate for here is going to be that 0.5625. Okay, check out the graph. If I graph e to the minus x, that's this right here. And you can see quite clearly that there is a root, maybe a little bit further than halfway from 0 to 1. So it looks like it agrees with our estimate. That's how this works. Now, let's go on and explore this a little bit more. We have one more example to do, and then I need to talk a little bit about convergence. So it's going to be a bit longer here, but what is the error associated with our estimates? That's going to be of importance. So suppose that we attach one extra little piece of data associated to each step of that algorithm, okay? We're gonna let n equals 1 correspond to the initial step, and that with each iteration of the scheme, we increase n by 1. So our first interval is n equals 1. Our second interval is n equals 2. Our third interval is n equals 3, and we arrived at a fourth interval that would be n equals 4. The error is halved every single time right? Imagine that if we chose the midpoint as our estimate of the very first interval, then we could be only half the width of that interval away from the true answer. But then if we have the interval every time, well, it's going to be only half of that interval, and only half of the one after that. And in general, it's going to be 1 over 2 to the n times the distance between a and b. So if I go back here, I just want to show you again what I exactly mean by that. Our current interval, our initial interval, in this scheme, this is n equals 1. After we carved it in half once, this is our second interval that we're considering. This is n equals 2. The next interval after that, this is going to be our n equals 3 interval, and our final interval that we got to is the fourth. So in this example, this first example that we did, we can guarantee that by taking the midpoint of that last interval, we can be no further than what, 0.0625 away, which corresponds to that quantity that I indicated on the next page. So let's fill in some stuff here. Our final estimate corresponds to the fourth interval, and so the error in that estimate is no greater than 1 over 2 to the 4 times 1, because that's the distance between b and a for our example there, which is 1 over 16, which corresponds to that 0.0625. Okay, so that's the most that our final answer could even be off by. So that was 0.0625. And it's nice to have a measure of that, because then you know how bad your answer can be as a worst case scenario. And that's good if you need to be able to guarantee a result within some tolerance, within some number of decimal places. It turns out the true value is about 0.567143. It keeps going on forever. The value we came to for our estimate was 0.5625. And so our absolute error that we get to, I think, works out to this. I wrote this down, hopefully I'm right, 0.04643. Excuse me. The relative error works out to, with just 3 iterations, 0.82%, which you could calculate for yourself. That's not bad. Considering that we only did 3 iterations, that's something a computer could do in a tiny fraction of a second, and in reality, you could do this 100 times over to get to a much, much more precise solution. Cool. All right, we're going to do this on one more example right here. And it's on this cubic. Use the bisection method on the function f of x equals 8x cubed minus 15x squared plus x plus 5, using a starting interval of -1 to 2. So we're going to do the same sort of thing as we did before. We are given an f here, so we're really just trying to find the roots of this thing. And we're going to do this one more time. It's going to be a bit of a pain in the butt, but that's all right. So, starting interval. Our starting interval is -1 to 2, our best estimate, right from the start without doing any work at all. You could test just fine that on one side and the other they're going to be on opposite signs. We'll see that in the first step here. Our best estimate is going to be halfway between the two, which is 0.5 for the x value. Okay, so let's start testing. We have f of -1 and f of 2. F of -1 works out to -19 if you plug things in, while f of 2 works out to 11. So we're on opposite sides. We're on way different sides. Like, we're not even close to 0 right now, so our answer isn't, we have a ways to go, that's for sure. And we're going to test the midpoint, which is 0.5. So f of 0.5. And if we do, if you plug 0.5 into the function, we get much closer. We get to 2.75. Okay, that's one iteration. And that means after one iteration, we have a new interval of, let's see here, which ones are on opposite sides now? We have a positive value here, so we need to look at the one that was negative before, right there. So it's somewhere between -1 and 0.5. So -1 and 0.5, and our best estimate at this point is between the two. And we're going to go with x equals -0.25, which is also going to be the next point that we test. But I'll rewrite this for organization. F of -1 was 19, negative 19 rather, while f of 2 is, no, that's not what we're doing. We're doing f of 0.5. That's equal to 2.75. We're going to want to test f of -0.25, the midpoint of the two. If you do, you end up with 3.69. Okay, we've carved down the interval a little bit more. It looks like we've actually come up from 2.75, but we have to be in a tighter range of x now because we have a smaller interval now. So there's got to be a root between those two. We've got 2 iterations finished now. And our new interval is -1 to -0.25. And I said do it 3 times, so we're going to do it one more time. And it looks like those two, we're going to have f of -1 still, and f of -0.25, like so. And we're going to test the midpoint of that. If you work out what the midpoint of that, the two of those is, I think it's -0.625. Yeah, I think so. So f of -0.625, and that works out to be -3.438 or so. With all of these, right, don't worry too much about precision on each step. The most important thing is just that they're on either side of that root. One's positive, one's negative. It doesn't really matter how many decimals you take. Okay, so that means we get to our final interval. That's 3 iterations. Our last interval is, let's see here, it's somewhere between -0.625 and -0.25. And that means that our final estimate, if we use the midpoint, is going to be directly between the two, and that's going to be, so our final estimate is x equals, and that works out to -0.4375. Okay, and again, bisection method comes with that error formula, and you can apply that here to see how far off we are. And I believe it would be 1/16 times the distance between those two, the starting interval, the bounds of that. So it would be like 3/16 or something like that. We have to be that close. Okay, so there's one interesting thing here. I want you, as homework, to go and graph this function. Okay, you can use graphing software or whatever, but you'll see we've answered the problem because the problem asks to find an estimate. Find an estimate for a root of f after iterating this process 3 times. But what it didn't say was find all roots. And you can have a function like a cubic that could come up, back, and around, and you could have up to 3 roots here. So when you're using this estimate, one thing you have to be really, really careful about is the fact that you might get to an answer, but we can only ever zoom in on a single answer. And you might miss out on others unless you have different kinds of initial intervals. So if a problem involves finding all roots in a particular interval, you might want to use some care. Try different intervals, try smaller intervals, and bracket smaller to begin with instead of a big, like our initial interval here was like 3 units long, and that might contain a lot of intervals, a lot of different roots. So if you use smaller intervals that bracket single roots, then you might be able to avoid this problem. And indeed, you can see here, here's the root that we centered in on. But here and here are roots we missed. So as a matter of fact, in this example, there are in fact 3 roots in the interval -1 to 2, and so that's what I was saying, that it might be a good idea to start with those smaller intervals so that only one root is contained. If you don't do that, then you possibly wind up with a case where you miss some of the information that's there. That's why I phrased the question in the first place, to try and coax this out, to see how this function might work, or how this process might work, rather, with a function that has more than one root in that interval. Okay, there's one other thing I want to talk about today, and it's not coding. We're going to save that for another day. I want to talk about convergence. It's a small conversation. It's challenging, though, because it involves kind of a tricky little definition. Ultimately, there are going to be a couple of times in the semester when we can calculate this quantity, but oftentimes it's something that's very difficult to calculate. It's a good idea to know, however, what the speed or efficiency of a method is, and that's what this is referring to. Because oftentimes it might be useful to know, well, which algorithms are most effective, which are most efficient, which are quickest at honing in on a solution. Okay, so we can measure this by something called the order of convergence. Okay, so here's how it's going to work. Suppose we have a sequence of estimates xk. So that is, we have an estimate every single turn of our different kinds of estimates that come. We're interested in how quickly our estimates might approach a result x star. More efficient methods produce quicker convergence. Okay, so to be precise, the order of convergence is a measure of this quickness that's obtained by comparing 2 subsequent distances. Okay, let's think about this. All of the xk's, all in that sequence of estimates, should be getting closer and closer and closer and closer and closer to the final estimate, what you're getting close to. Okay, and those should get so close eventually that that distance shrinks to 0 if they converge to a solution. But the question is, how quickly do they do this as you iterate that procedure forever? And one way to do this is to compare 2 different distances. The kth estimate and the final estimate, xk and x star, and the estimate before that and x star, xk minus 1 and x star. So this is the distance between the kth estimate and the final result. And this is the distance between the estimate before that and the final result. This one should always be closer than that one if our estimates are getting better and better and better. The question is, how much closer? How much smaller is that first one than the second one? How much smaller is the first quantity than the second as k grows large? Now, it's interesting, right? Because it might depend on k itself. Here's how we do just that in terms of the math. So the sequence of estimates xk is said to converge to x star with order p if as k grows large, there's some sort of constant lambda such that this relationship is true, that the distance between the kth estimate and the final estimate is roughly equal to that constant times this estimate right here, raised to the power p. Or, similarly, if this quantity, this ratio, gives us a constant, roughly, as the k grows large. I want you to think about this a little bit. This quantity, again, should be smaller all the time than this quantity right here. forget the p for a second. Okay? Imagine that the p is equal to 1. Maybe with every successive estimate, the distance you are to the final solution is halved and halved and halved and halved again. Then this relationship is always going to be that the top is half the distance of the bottom. That means that you would get, as k grows large, a constant value right here. So if that distance was halved and then halved and then halved again, that's going to converge in on the order of p equals 1. Okay? But you get faster convergence if the p is larger, because that means that, relatively speaking, imagine that these are both small quantities to begin with, that you have to take this small quantity to a higher power p to make that relatively smaller top. So if that p is a larger number, then to make sure that the result is a constant, well, it's got to be the case that the xk is, relatively speaking, much, much closer to the x star even then. So this p exponent, the higher the p is, basically, the more the distance is shrinking, and the more quickly it's shrinking with every successive estimate. That's how we measure this order of convergence. It's a really tricky definition, and it's very hard to actually calculate by hand. It's only in a very few cases that we can do that. In fact, it's much more easy to kind of estimate what this is by looking at data for a lot of different functions, a lot of outputs, and so on. So typically the value of p must be estimated from observing the actual output from an algorithm. Okay, the important part for you for now is the larger the p is, the faster the convergence. If p is 1, an algorithm is said to converge linearly. If p is equal to 2, the sequence converges quadratically, maybe not so surprisingly. In general, the higher the value of p, the greater the relative difference between those two quantities in that ratio, and therefore the faster the convergence. Bisection method, in particular, is really helped by the fact that we have a very predictable set of intervals to think of, and therefore a very predictable upper bound on the errors. So it's pretty easy to see that typically, at the worst, if you have the next estimate, well, you've got to have the greatest possible error possible, the greatest possible error from the step before it at every step, right? You might do better than that, but at worst, you're getting to half the possible error. And so this ratio, which is exactly the one that appears on the last page, but with no exponent right here, has to tend to 1/2, because the quantity on top can be no bigger than half the size of the quantity on the bottom. So this quantity on the last page, but with p equals 1, tends roughly to 1/2, a constant. And because that p is equal to 1, we don't raise the bottom to any exponent to get that distance on the top. The convergence is linear for bisection method. In terms of schemes, that actually means that even though we'll be guaranteed to get to a nice result, that's actually going to happen a little bit slower than it will for some of the other methods that we're going to talk about. And again, it's very hard to measure and to even understand what that ratio is saying, although I tried to do my best to kind of explain what it kind of means. For you, the most important thing is to know that for bisection method, p equals 1, we have linear convergence, and as we go into future methods, those are going to be improved. So let's wrap this up here. It's been almost 40 minutes, so it's been a bit of a long process here. But bisection methods, I think, pretty easy to understand, especially if you do it once or twice. A few of the for you to try problems for this section are really about you coming up with functions using whatever graph sketching knowledge you have, testing functions in different graphing software you might find online or in MATLAB itself, and then trying to use these schemes to estimate where roots might be found. But we're going to see that there are some more sophisticated routes towards doing this. Instead of by hand, you can code this stuff, and it's not that hard to code. So we're going to talk a little bit about coding this in a future lecture, and we will be talking about some faster methods of coming up with roots for different kinds of functions, and 3 other methods, one called false position, one called secant method, one called Newton's method. You're going to have to know them all. None of them are terribly difficult conceptually, but some of them are really interesting. So my advice to you right now is to get down this one, because it is relatively straightforward and can be used for a lot of simple problems. And we're going to bring it in with the next lecture where we talk about how to program this stuff. Okay? For now, take care of yourselves. Ciao, and I'll see you in the next one.